In integral calculus, complex numbers in Euler's formula may be used to evaluate integrals involving trigonometric functions. Using Euler's formula, any trigonometric function may be written in terms of eix and e-x, and then integrated. This technique is often simpler and faster than using trigonometric identities or integration by parts, and is sufficiently powerful to integrate in any rational expression involving trigonometric functions. Euler's formula. Euler's formula states that substituting minus x for x gives the equation. These two equations can be solved for the sine and cosine. Simple example. Consider the integral. The standard approach to this integral is to use a half-angle formula to simplify the integrand. We shall use Euler's identity instead. At this point, it would be possible to change back to real numbers using the formula e2x plus e minus 2x equals 2 cos 2x. Alternatively, we can integrate the complex exponentials and not change back to trigonometric functions until the end. Second example. Consider the integral. This integral would be extremely tedious to solve using trigonometric identities, but using Euler's identity makes it relatively painless. At this point we can either integrate directly, or we can first change the integrand to cos 6x, 2 cos 4x plus cos 2x and continue from there. Either method gives using real parts. In addition to Euler's identity, it can be helpful to make judicious use of the real parts of complex expressions. For example, consider the integral. Since cos x is the real part of eix, we know that the integral on the right is easy to evaluate. Thus, fractions. In general, this technique may be used to evaluate any fractions involving trigonometric functions. For example, consider the integral using Euler's identity. This integral becomes, if we now make the substitution u equals eix, the result is the integral of a rational function. Any rational function is integrable, and therefore any fraction involving trigonometric functions may be integrated as well.